Alright, hell yeah. So we're going to answer the question, what's the impact of dropping something from zero height? You know what I mean? And I guess the first thing we're going to do is just show you with energy of just how ridiculously simple the energy equations are. But they're not intuitive. So the next thing we're going to do after we do energy is we're just going to take this same block and be like, hell yeah, it's the same thing as just placing it on a spring. And we're going to say, hey, this spring is actually just this length anyway. You know what I mean? That's its L naught or natural length. And then we're going to just hover this mass over this spring and then let go. You know what I mean? So that's dropping it from, technically, for impact loading, that's dropping it from zero, from zero height. Because usually you bring it up a height and then drop it. So what we're going to do is our chunk of mass is just going to be right down here. It's not going to be resting though. We're actually going to lift it so it is not touching. So you know the example would be this. You know, I mean, here is the platform of our spring, and you can just imagine that there is zero. You know what I mean? This is 0 millimeters, but we are holding that mass up and then instantly letting it go, and then we're gonna figure out the impact from that. Now, the straightforward approach is just, well, if we just hold it at that height and then slowly, you know what I mean, just very ever so slowly, just relax it into the spring. I guess, yeah, we'll do this. And if we do that, we get this change in length. You know what I mean? But the take-home message, hey, that's going to be our change in length. The take-home message is if we hold it right here and then just let go and impact it just with its own weight, we're going to see that the change in length is 2 times this change in length. You know what I mean? So we'll basically have a 2 times change in length type of scenario going on. Okay, hell yeah. So, I guess the first question, before we do energy, the first question is, well, what is this initial change in length? So we write the strength. We're dealing with material mechanics, so you have to write all these equations out. I would write them every time. Strength is force over area. Stretch or strain is change in length divided by length. And then the relationship between these, you know what I mean, is strength is modulus of elasticity times E. And now we can take these two and then insert them into here. And so we get F divided by A is modulus of elasticity, change in length divided by L. And then what we want to do is rearrange this for force. I'm sorry, no. We're more interested in change. Yeah, it depends on what you want. You know, we're actually just interested in change in length, so let's just go for it. Change in length, and this one's pretty easy. FL divided by EA. The L goes up top, the E goes downstairs, and I don't know, maybe it spells flea, going that way. But hell yeah, so we can find that initial change in length. I mean, we can just find the change in length of this rod just by holding that mass on there. So let's do that, and that's going to be the force that we're the force. Well, the force of that is just the weight of gravity. You know what I mean? So if we have this mass, the force on it is the force of gravity, and that's mg. So cool. So we have mg L divided by EA. And even the area is the cross-sectional area. We could do pi divided by 4 diameter squared. But anyway, so here we go. So let's do it. So we have a 20 kilogram mass times 9.81 for gravity, length of 2 meters divided by modulus of elasticity. It's in gigapascals, so this is 210 times 10 to the 9 pascals. And what the hell is a pascal? It's a Newton meter squared. You know what I mean? Because then our units will cancel out, but we're going to go 210 times 10 to the 9. And even on this one, I'll do Newton meter squared just because all the other ones, you kind of know what they are. You know what I mean? We're going to have area in meters squared. So we do have to get our diameter. This is going to be 0.015 meters. You know what I mean? So 0.015. And hell yeah. So we can do it. Alright, hell yeah. Sorry about that. Somebody was at the door. So anyway, where are we at? Are we typing this thing in? So we have 20. I'm just going to do it like this. Sometimes I don't want to... okay, check this out. So in the calculator, we're just going to do 20 times 9.81 times 2. Now I'm going to divide. I do have to do a parentheses for this, but I don't really, you know what I mean? Like, let's say I didn't want to do a parentheses for this every time. Well, this is just divide by 200, but then I still have to do divide by 10 to the 9. And this is cool because it gives you kind of that mathematical fundamental understanding of, like, you know, kind of what you're doing. You know what I mean? You're dividing by, there's a product here. You have a product of 210, and then you have a product of 10 to the 9. You know what I mean? And then you have a product pi divide. So these are all products. So in my calculator, I just have to do the divide time every single time. So and even right here, let's say I just wanted to divide by pi and then get technical, I just now multiply by 4. So weirdly in my calculator, I just do that and then do another divide by 0.015. So I probably just tripped a lot of people out, but it's just kind of cool to mix it up, spice it up, and we get a change in length. And it's probably wrong or whatever, but we're going to multiply by 1,000. Oh, holy Toledo. It probably was, you know what I mean? I probably messed something up. So, well, let's not do that and do 20 times 9.81 divided by 2. And now I'm going to divide by the whole thing. 210 times 10 to the 9 pi divided by 4, and then 0.015. Oh, no, duh. No, we were just fine. It's just, I'm glad. Anytime you feel like you have an error, you know what I mean, throw some asterisks on the board, because you will talk yourself out of that error so fast instead of just looking for it, you know what I mean? So, yeah, we can go back to this. We were jelly, and we just had to take this squared, you know what I mean? All right, booyah. So, and then we're going to multiply by 1,000. This is how many millimeters, and we get 0.057 millimeters. You know what I mean? So just the actual resting weight of it, and I feel like oh, and now I know, because I was just like, why does this feel just a little bit off? Because in one of my problems I did 10 for gravity. And, well, times 1,000. Now, I still think I'm a little bit off. So let's slow down here, and actually, we want these to be fairly accurate. All right, hell yeah. So, no, we're right on, you know what I mean? But this was the answer. It was 0.0106, and that's exactly what we got, 0.0106 millimeters. Sometimes you love sample problems because you need that check on reality. Because if you've not done problems like this, you don't have any way to kind of like double check what the reality on this is. But we do. So let's go over that, because you're just like, well, how could you double check that this number is 100% accurate? You know what I mean? What's just another way to do this? And we go back to the fact that, hey, we know, and you just have to know this. It's not even in the problem statement, but the max strain for steel is 0.002. You can stretch it 0.2% of any given length. If you do have 1 meter, that's 1,000 millimeters, and you stretch it 0.2%, that's going to be 2 millimeters. Because just think about it. If 1,000 millimeters, well, what's 1% of 1,000 millimeters? It's 10 millimeters. You know, and maybe that's not a very good. If you have 100 millimeters, what's 1% of this? Well, that's going to be 1 millimeter. Okay, so now what's 2%? That's going to be 2 millimeters. Okay, but we don't have 2%. We have 0.2%. So what's if we start with a length of 100 millimeters, what's 0.2% of this? Well, that's going to be 0.2 millimeters. But you know what I mean. So that's for 100 millimeters. Now, what's 1,000 millimeters? You can kind of do that same thing. You know what I mean? Let's say your bill at the bar is $1,000 because you bought everybody rounds. You know what I mean? And you have to do a 10% gratuity. You know what I mean? It looks like you're going to be shelling out. Holy hell, you know what I mean? What's 100%? You know what I mean? That's $1,000. So what's 10%? It's $100. Damn, I had to think about that. You know what I mean? So that's 1%. Now what's 0.1%? Well, that's only $10. Sweet. So, is that right? No. I just said this was a 10%. Holy Toledo. Yeah, sometimes percentages are a little bit interesting. But we're pretty good at them because at least if it's a positive range. You know what I mean? You could probably do 1%. You can definitely do 10%. You know what I mean? 20% tips the gold standard now. But anyway, so 10% of $1,000 bill is going to be $100. What's 1% of that? That's where I wanted to go with this. That's $10. Now, what's 0.1%? Well, that's $1. You know what I mean? So, out of a $1,000 bill, 0.1% is 1 millimeter. You know what I mean? But what's 0.2%? Well, that's going to be 2 millimeters. Or for our case, it's going to be $2. You know what I mean? $2. Okay, hell yeah. So just getting used to steel is 0.002. I don't think anyone's going to know what the hell that number is. And just saying it's like too small. Like humans, we hate small numbers. But changing to a percent, 0.2%, it's halfway tolerable. You know what I mean? Okay, I kind of get it. So with that said, you know what I mean? If I have 2,000 millimeters, you know what I mean? What's 1% of this? Well, that's going to be 20 millimeters. So what's 0.1%? That's 2 millimeters. Okay, but now we need to do 0.2%. So maybe we should start this whole thing by saying if my bill is $20,000, you know, high rolling, and I got to do 20% tip. Okay, so I know what a 10% tip is. That's going to be $200. So I just double it. It's going to be $400. Cool. But I'm not giving a 20% tip. Let's do 2%. You know what I mean? Hey, now that's $40. Okay, and I'm not giving a 2% tip. I'm giving a 0.2% tip. You know what I mean? Just something. I mean, something. And then that's going to be $4 for this case. So I don't know. I just think it's really good to get used to thinking of this as 0.2%. That can be useful. Or just 0.002. And you have an equation. You know what I mean? Hey, throw in length right here. You can either throw it in millimeters or meters. And then you know that this max is 0.002. So you can find your change in length. So change in length is going to be strain max times length. That's going to be 0.002 times 2,000 millimeters. You know what I mean? So it should be obvious we get 4 millimeters. Okay, the whole reason I was doing this is because from that we can get a check on reality. Because we can also find the strain max. And sometimes finding the max strength isn't super useful. You know what I mean? Like sometimes we might want to find the max force. Well, you have this equation, and let's talk about this. Because once you get these two and then this relationship, you can throw all these together. So let's rewrite this one. We have F divided by A is equal to E change in length divided by L. Now of these, what can we put subscripts on? Because here, we can say, hey, this is max and this is max. But we don't put a subscript on area. That's already given for our problem. Same here. We can put max change in length, max strain, and then here's our length. So that's going to be the trickiest thing doing material mechanics, is knowing that these can be max or these can be less than max. You know, maybe allowable. Or you know what I mean? And anywhere in between, from 0 to max. Okay, so on this equation, yes, the F can get a subscript, max. Area, no. E, modulus of elasticity, just by definition is a constant. If we're dealing with steel, this will never change for this particular type of steel, let's say. Okay, now we have change in length max divided by length. Okay, sweet. So if I wanted to find the max length, and then you know what I mean? And you don't have to take the equation this far, because you know that this is E. So this is also, I mean, this right here is also E max. And that's what we just said was 0.002. So for our problem, we can say that force max divided by area is modulus of elasticity times E max. But it's just fair, it's fascinating. You're going to have to do this on your own and be like, whoa, you know, we have these two equations and this that relates both of them. And then you can put them together to get an equation like this. You don't have to have this equation in its form, because this you could just say is, you know, the strength or stress times E change in length divided by L. Or you could keep it as F divided by A, but then change this to just the strain. You know what I mean? Strain times modulus of elasticity is force divided by area. And maybe you could rearrange to get force. You know what I mean? And so that's kind of what we're doing. We're saying force max divided by area, modulus elasticity times strain, and we can rearrange this to find that force max. That's going to be EA sigma max. But even right here, I think we've lost like all touch from the problem. So this equation is kind of the gold. What this says is, this basically with the modulus of elasticity says if you have 4 millimeters for our scenario, we are going to generate a max. You know what I mean? So hell yeah. And the max for this is 0.002. So we're just going to take 0.002 times 210 times 10 to the 9. That is going to give us the max strain. So that would probably be, after all that, that's probably just the easiest thing to do. 0.002 times 210 times 10 to the 9. Heck yeah. And divide this by 10 to the 6 just to see what kind of number it is. And for sure, we got 420 megapascals, which is 420 times 10 to the 6 newtons per meter squared. So that's the max strength or stress in units of like American units of PSI, but it's force per unit area. So this is the max. This is associated with 4 millimeters. Okay. But for our problem, that really doesn't help us. We really want to know what the force is. So, but because we have this, we can just then use, we don't have to do the equation all at once, you know what I mean? We can just find, hey, what's the strength max? And now we can throw it in here and find what's the force max. And any of these equations, you know what I mean, they're kind of like 3 different things. You can arrange them 3 different ways. So we're going to rearrange this for force max. Just bring the A upstairs. And so we have force max is that 420 megapascals. It's times 10 to the 6 Newton per meter squared. Hell yeah, times the area. That's going to be pi divided by 4 times 0.015 meters. Holy Toledo, got to make sure to square that. And we got 420 times 10 to the 6 times pi. Times pi divided by 4. And then times 0.015 squared. Cool, so we get the force max as 74,220 newtons. And now, this is the max force you can, so this is synonymous with 4 millimeters. You know, that's the whole point of material mechanics. You're saying that any given material is a spring until you reach this max, and then it's no longer a spring. You're going to kill people, or, you know, you're going to make decorative steel because you're going to bend it, and cool, it bends, it still holds strength. But, I mean, the second, like, a bridge reaches these elasticity, not like the max, it passes the elastic range, then, yeah, probably people are going to die. So anyway, so we just stay within that range. That's why this max, is very crucial and important. You know what I mean? For most problems. Now, there's specialty problems where, hell, you know what I mean? You can, this 0.2% is very potatoes compared to what you can actually stretch steel. You can stretch steel 5%. 0.2 compared to 5%. That's 5 divided by 0.2. That's 25. You can stretch it 25 times what you think you can stretch it, but you're not getting any more juice. So these problems are very specific. You know what I mean? They're indeterminate problems where one of the members does hit its max and is in a state of past its elastic. It's in deformation, but other bars and other members, are in a state of elasticity. If everything isn't in a state of elasticity, you are royally getting fired and probably killing people. But there are those specific problems where, one member, just because you have, you can't make everything determinate. So if you have, just with the, and it's interesting. Those are fascinating problems to explore. Just because you're like, whoa, I thought we can't take anything to the max. Well, in those, sure, one is just going to, by happen chance, go to the max. Because in your fit up, even this, if you have like an industrial size stuff, and this is like a two meter, you know what I mean, like bar, and then your fit ups aren't within a tolerance of 4 millimeters, you know what I mean, you might put an undue 5 millimeter stretch just because one of those bars is trying to take the whole load, and it might be, you might have 5 bars in a row, you know what I mean, indeterminately connected, you know what I mean, at joints where, you know what I mean, there's one just happens to be like taking, like one has to stretch by 4 millimeters, or 5 millimeters before the others can actually do a damn thing. You know what I mean? So for sure, that one is going to pass its elastic range. Cool. So I do like involving those things in my videos where you're just like, yeah, what is the next step? But okay, so back to just the easy stuff. So we have this max force of 74,220 pounds. It's synonymous with 4 millimeters. When we have this weight of 2 kilograms, we have an earth underneath us. I love going back to F equals ma. So we identified a mass, that's this side, and we want to know the force on that mass if it's in a state of acceleration, you know what I mean? And, I don't know what the hell. I don't know if this is a good time. But anyway, I'm just gonna balk and say, hell yeah, we all know that force of gravity is mass times mg. So for sure. So if this mass is a mass near the surface of the Earth, it's going to, at the center of its mass, it's going to have a force down on it of mg. And then that's the only thing. If it's just resting on this spring, that is the only force that's going to be, you know, that mass. Oh, and then so for the spring, the only force the spring feels is that mg. And then so let's determine what that force is. You know what I mean? Force of gravity is mg. That's going to be that 20 kilograms times 9.81. So cool. So we have 20 times 9.81, and we get 196.2 newtons. So now here's the relationship. I can put a force of 74,000 newtons, but if I'm just resting that mass on what we call a spring, the steel bar, I'm only generating 196.2 newtons. You know what I mean? And I think most people are actually horrid at like mentally being like, what is the millimeters that's associated with? You know what I mean? If 4 is to 74,000, what, like, that's like SA, or you know what I mean, like SAT, I don't know, just kind of like IQ stuff. I think people are absolutely horrible at this types of stuff. So how do we take this and just for sure get it 100% every time? Well, yeah, this is going to be like an equivalence. You could put an equal sign here, even though the units don't match up. But anytime you have an equivalence that you're going to write long ways, you know what I mean, don't do it that way, or do it once, but then stack them. You know what I mean? So write 74,200 newtons divided by 4 millimeters. And write it again. Write it in the opposite. 4 millimeters divided by 74,200 newtons. Because if it's your first time at the rodeo, you know what I mean, one of these is useful, the other one's not very. So over here, we have 196.2 newtons. What we want to get is millimeters. So we're going to use this one, and I'm going to show you why. Because we have 4 millimeters on top, 74,200 newtons on the bottom. We stacked them. This is the factor label method. We're saying this is synonymous with the number 1. You know what I mean? These things are equal. So then if we go over here and then multiply by 196.2 newtons, hell, newtons cancel, and we're left with the units of millimeters on top. And this is my check on reality. So all that with the explanation, it is going to be my check on this equation, which is just like, I don't know. I don't think anyone's going to trust their answer popping out of there, or there's going to be no way to back it up. You know what I mean? So, but here's your way to back it up. We have 4 divided by, well, I'm gonna store that in my calculator. I think it's already stored as alpha f. Sweet. So we have 4 divided by alpha f. Now times 196.2. Cool. And so we get millimeters of 0.0157. You know what I mean? Millimeters. And that's exactly what we get. So hell yeah. So we have a check on reality that this equation jives. And this was just resting the mass. It doesn't even really get to the impact of dropping it from 0 height. So, you know what I mean? I probably should have just done the energy, but this was a pretty good introduction. You know, always a good introduction to material mechanics. So, let's get another sheet of paper, and then... Alright, hell yeah. Alright, so let's do it from the energy perspective. And I think we need to set it up like this, with some actual height. If we set the potential energy here, and we're going to set our datum just right there, which isn't going to be true for our problem. You know what I mean? So this is just the way to... so let's do it. So the potential energy is at a mass, gravity, and then, so it's mgh, you know what I mean? And then the kinetic energy, this has to equal. So if that's our potential energy and we drop it, it's going to equal to the kinetic energy right before impact. That's going to be 1/2 mv squared. And then the spring energy of the spring, is going to have to equal the potential energy. Why? Because we're saying the spring, you know what I mean, this steel bar is going to stop the velocity. You know what I mean? So we're not going to have any velocity once this spring is maxed, the max stretch in the spring. And so we're going to say this is 1/2 k change in length squared. All right, sweet. But this isn't exactly what happens, because if we do have a change in length, well, then our datum is we're going to have some sort of delta L change in length, and so we have to take the datum from there. That's if we're talking about potential energy, that would have to be our datum. So our mgh would be mgh plus change in length, and this is how they have it written in the textbooks. And then so you can say these two things are equal. Okay, and if we did this, the textbook approach is just to say, well, if we drop it from no height for our scenario, you know what I mean, just hover it above that gripping part of the bar, you know, weightless, you know, because we're holding up that 44 pounds and then just instantly letting go. Then we are going to, it's going to instantly put the weight onto the spring. And so back to this scenario, you know what I mean, if we do that, it's going to cause, this mass is going to change its velocity. Its velocity is 0. It's going to reach some sort of max velocity about halfway, maybe not halfway, but anyway, and then the spring is going to apply a force to stop that change in velocity. So right after so F equals ma says, hey, we have a force of gravity down, and then there's no resistance. Even though you're right at the edge of the spring, just think of a spring, that first little bit of deformation, change in length, almost puts up no resistance force. So that force of the spring resisting is just basically 0. So you essentially have the acceleration of gravity right off the bat. You have a change in velocity of 10 meters per second just for a very short amount of time, not a full second. So this thing's not going to go 10 meters per second, but you might have 10 meters per second squared. I'm sorry, it's got to be 10 meters per second. But you might have that for a 10,000th of a second, you know what I mean? And if you have it for a 10,000th of a second, you're going to generate some sort of velocity. And if you have some sort of velocity, the only thing, F equals ma says, the only thing that can change that velocity is a force. And that's what we see. The spring does provide a force, and it has to slow that velocity. But the spring, when it starts off, has a very small force, so it can only change that velocity. So you can model it where the force of gravity is going to be bigger than the spring force for a small displacement. But you can see that if we have a displacement of 4 millimeters, we can generate a huge amount of force compared to just the 200 newtons that's generating from that mass. All right, hell yeah. So, anyway, so that's kind of the F equals ma. It's just very fascinating that this mass will change its velocity. It'll have definitely some velocity, but we know the spring is going to make that velocity go back to 0 because that spring force is going to be, it's going to be, at some point, the spring force is going to be equal to the force of gravity. That's when it's going to stop changing velocity. That's when it's going to reach its max velocity. But then the spring force, upon more compression of the spring, then this will definitely get higher, and so then it'll have a change in velocity the other direction. So then we will be slowing it down. You know what I mean? So up to where force of gravity is equal to the force of a spring, that's like a skydiver, where the force of drag of the air is going to be equal to the force of gravity. You know what I mean? We've already got up to some sort of velocity terminal. But there's nothing that's slowing us down. But with the spring, hell yeah! Then we get to a spot where the force of the spring is greater than the force of the gravity, and so that will slow our velocity. And then when that happens, at the end, when this thing does stop, you know what I mean? Don't forget, this is higher level, engineering. That, now you still have a tiny force of gravity down, and you just built up a huge force of the spring. And so now this has a net force that direction. You've identified a mass, F equals ma. Now you're going to have a change in velocity that way. This thing is going to compress and then start, even if you just drop it, it's going to go that way, reach a max speed. The spring force is going to slow it to a stop. Once it does that, now the spring force is like hella, and then so it's going to cause that thing to go with the velocity back, and you basically will just get oscillation. You'll get oscillation from here to how far it's going to deflect. And if there's nothing to resist that oscillation, no friction in the system, it'll just do that. Hell yeah. So it'll just do that forever. You know what I mean? It'll just go back and forth forever. But we could care less about oscillations. No one cares. Unless you're in 400 level classes and stuff. It's fascinating. I would appreciate a class on it, actually. But we're just saying, hey, when is that going to stop? We get it. We get one cycle. It's going to generate some sort of velocity and then stop. All right. So back to the energy of the spring. The energy of the spring is going to equal potential energy because our kinetic energy is nothing. You know what I mean? So at this moment, when the spring is totally has all the energy, there's no potential energy because we set our datum to be so, and there's no kinetic energy. You know what I mean? So the initial energy of the system, energy can't be created nor destroyed unless it's removed from the system, but all the energy is still in the system. We got that potential energy, dropping it. It's going to reach that's going to equal the kinetic energy upon impact, and then that's going to equal the spring constant. So yeah, we have a very fascinating problem that we can actually dive more into later with this kinetic energy, because what we're saying is that the kinetic energy is, if we just hover it above that location, we're going to say it has a potential energy. Now our potential energy is just mg change in length. So this equation just says, hey, this is 0. And now we have mg change in length. And we're going to say that's equal to 1/2 k change in length squared. Cool. And we'll see. At the halfway point, we already said at the halfway point, you're going to have a max velocity. We just, I don't know. I think it's going to be the halfway point. I would bet it is, but I for whatever reason I'm not quite sure. You know what I mean? Sometimes it's hard to know if there's a linear relationship or like a square relationship. And so that's why I'm having a hard time saying, like, well, where does this thing get max velocity? It seems, I don't think it's going to be the halfway point. So anyway, so let's just stick to the problem of that from the energy equations, I mean, the fact that it makes it easy, right? So we just get to it. These two things are going to be equal. Okay, hell yeah. Enough said. So we can say mg change in length is equal to 1/2 k change in length squared. Well, hell, we can cancel one of those, cancel one of those. We can solve for change in length. This 2 goes upstairs, 2mg divided by k. So cool. I'm just going to do it in one step. So we have 2mg divided by k. That's all I did. I got rid of one of them. That gets rid. 2 goes up there is 2mg. And then I just rearranged the equation to say change in length is 2mg divided by k. Yeah, obviously the k goes downstairs too. Alright, so hell yeah. But now here is where you need to go back to your your material mechanics equations. Strength is force over area. Strain or stretch is change in length divided by length. The equation that relates these is strength is equal to modulus of elasticity times strain. So then we can put those equations together and say force over area, modulus of elasticity, change in length divided by length. And this is the first one I would do. I would get force all by itself. So A goes upstairs. We have EA. We're going to divide by L and then put change in length kind of off to the side. That's all we did, rearranged. And you can see that this is synonymous with the force of a spring. This is K, change in length. So with materials, steel, concrete, wood, you know what I mean? Hey, and in the elastic range, this value is your K. So we have spring constant is modulus of elasticity times the area divided by the length. Cool. So this value is what we put into here. And now we got change in length is 2 mg divided by EAL. Hell yeah. And that's it. So from this scenario, this should give us, and now how is this going to double us up? You know what I mean? And why does this double us up? And how can we show that this is twice the value? You know what I mean? Just with letters. I'm just curious from this. So, and why did this work? Is because we used the energy equation. We said that if we have this much potential energy, it has to equal the amount of change in length of the spring. You know what I mean? And because we're dropping it from a height of the change in length. It doesn't look like we're dropping it from a height because this spring isn't, you know what I mean, sprung. You know what I mean? It's at its natural length. But the second we drop it, this spring will lengthen, and that means this mass moves down just a little bit, and it's the change in length. So that's the potential energy there. Okay, so then the problem is just like, well, you have to think about this. Let's say I just take this weight and just ever so gently, because, okay, so for this problem to work, you have to hover the weight at 0 height and then instantly let go. You know what I mean? Just instantly shock load that 44 pounds, 200 newtons, onto that rod. Okay, so you can imagine a scenario where you don't just shock load it, you just let it down gently. And again, if you do shock load it, it's going to vibrate back and forth. It's going to have a max change in length to stop that momentum, and it's going to vibrate back and forth. Obviously, that's imperceptible, and you might not even know it's going to vibrate. But now, if you just took that mass and just very slowly set it onto that, you know, spring or rod, then it's going to have a velocity of 0 when you let go. You know what I mean? It's already going to lengthen the spring, and all we have to do is just go back to our material mechanics equations, and we'll write them again because this is just so good. Strength, force over area, change in length. Strain is change in length divided by length, and what relates them? Strength is modulus of elasticity times strain, and you got force over area is equal to E, change in length over length. And what the hell are we trying to find? We want to know change in length. So change in length is just going to be FL divided by EA. And this one you should memorize by heart. Maybe it spells fleet. I don't know how you're going to memorize it. This is like, oh, okay, I'm on the right track, and we have change in length. And so let's do that. So we know that change in length, just for lowering it down ever so slowly, is force length divided by EA. And that's what kind of tripped me out here. What's the force? You know what I mean? The force is going to be the force of gravity. That's mg. So cool. This equation becomes mgl divided by EA. And now you can see this is 2 mgl divided by EA. So hell yeah. And most videos would just stop there. But we'll actually run through this equation. So we got 20 kilograms, 9.81 meters per second squared. Length is 2 meters, divided by modulus of elasticity, 200 times 10 to the 9. Write this as Newton meters squared, because then you can, that's just the only, yeah, I would never write it any other way. And then we have pi divided by 4, diameter is 0.015 meters, we're squaring that. So now these meters squareds will cancel. A kilogram meter per second, that's the definition. Always write this, F equals ma, and this is going to be Newton is equal to kilogram meter per second squared. And you can even say 1 Newton is 1 kilogram. 1 meter per second squared. But anyway, so if I have a kilogram meter per second squared, these units become Newton. Newtons will cancel, meters cancel, and now we're just left with this unit of length, and that's what we want. Okay, hell yeah. Okay, so let's do this. 2 times 20 times 9.81 times 2 divided, now we'll do it stealthy. 210 divided by 10 to the 9 divided by pi times 4 times 0.015 squared. I think we got away with one. Oh, hell no. Like, what are we doing so wrong on these? You know what I mean? Well, let's catch our errors. I don't get why. Okay, so we have 2 times 20 kilograms times 9.8 times 2 divided by 210 divided by 10 to the 9 divided by pi times 4. Oh, see. Oh, yeah, this method sucks. I have to divide by, see, I had to divide by the, I want to do this method more because I don't want to do the whole parentheses thing. You know, I just want to do it in this cool way, but holy hell. So, okay, so now we got the right answer. Times 1,000, and we get 0.0211479 millimeters. Divide that by 2, and we get 0.01057 millimeters, and so that's a check on reality. 0.0106 goes to 0.0212, and that's what we have, 0.02, well, you know what I mean. Not quite, but yeah, it is. If you don't round, it's exactly double. Okay, hell yeah. So now we're gonna finish this video of kind of how I wanted to start the video, but no one likes Excel. So we are going to. I'm gonna get some more time on the clock. All right, hell yeah. So this is so cool because I'm gonna answer my own question because we're gonna model this where, you know what I mean, we have the mass, and then it's going to fall from a height, you know what I mean, and this is going to be our change in length. So now we're really scaling this change in length up, and we know right off the bat it's going to fall in free fall. We have a force of gravity on this mass of mg, so that's the force down. When the spring is at its full length, you know what I mean, at the initial condition, there's no force on it. Even just for that split second, it's falling in free fall. So we know from our energy, potential energy is mg change in length. And this is fascinating where energy is, I like to do things with F equals ma, not because it's harder, because it tells you actually what's happening. Because I wanted to know if the velocity was going to happen right in the middle. You know what I mean? So, and I just didn't know. But here you go. You can say that the kinetic energy of this is equal to whoa. No. Maybe this is more complex, but this is fine. We're going to use physics to answer these questions. So we know that the energy of the spring is going to be 1/2 k change in length squared. And my question was, well, at what point is the kinetic energy 0? Because we know the velocity. Oh, no, that wasn't the question. That wasn't the question I wanted to ask. I wanted to know at what point is the velocity max, you know what I mean? And let me think about this one for a second. Alright, hell yeah. So let's come back to that question in the end, but we can solve it with Excel. Because what I wanted to show is that if you just use the F equals ma approach, what this gives you, when you rearrange this equation, you get acceleration is force divided by mass. And you'll actually get a number for acceleration. Now, you got to be careful about this because this is the summation of the forces is equal to the summation of the accelerations. You know what I mean? So it's the force net is equal to the mass that we're analyzing and its acceleration. So we have to write force net here. So right at the very beginning, the initial condition, you know what I mean, acceleration at the initial condition, well, it's only the force of gravity. So you have mg divided by m. You know, I should have, you know, said, hey, the force of gravity is that the only force. divided by m, and we know the force of gravity is mg, and we're dividing by that m, so the acceleration initial is just g. It's 9.8, 9.81 meters per second squared. That's the acceleration right off the bat. Now, this is why you should do this in Excel, because we're going to put some time values on this. So we're going to go 0, and I think I'm going to do like a 10,000th of a second, maybe even a 100,000th of a second, but we'll see. So in a 10,000th of a second, now the next position is x, and I guess I'm just going to call this x is equal to 0, and we're going to x is equal to change in length. That's kind of what we're analyzing, so we throw in 0 there. We want to know the initial velocity. Well, right off the bat, our velocity is 0, and then so the next row you want to write acceleration, and this is the equation. You have an equation for acceleration that says, hey, you got to because even right here, this isn't, the equation for acceleration says that we have a spring force up. You know what I mean? And so if we go back to F equals ma, we have to figure out, we're analyzing that mass, and we want to know the equation for acceleration, but we have to look in our textbooks of all the known forces. We have an Earth underneath us, so we do have an mg, and I'm just going to say that's going to be in that direction, okay? And then, so this is, I guess this is going to be the positive direction, but we have a force that's opposite of it, so negative sign, and that's going to be the spring force, and that's going to equal to ma. And then we go over here, like, what the hell is the spring force? Knowing if we treat this as a spring, we know that the spring is spring constant times change in length. And then for material mechanics, we do that whole thing to get F divided by A is modulus of elasticity, change in length divided by length, and we rearrange for force is to EA divided by L, change in length, And so we get something that's identical. From material mechanics, we say EA divided by L is change in length, and this is our K value. Okay, and so we just want to input that into our equation. So we have mg minus EA divided by L times the change in length. And the change in length of the spring is for our diagram is going to equal this x. So if we're saying this is x is equal to 0 to x, so now we can actually put an x, we can just say, hey, that's EA divided by LX. You know what I mean? And we're going to say x goes from 0 to change in length. Cool. So now we have, from the physics perspective, we have a cool equation with a variable that can be changeable. And we say that those are the forces, and that's going to equal to ma. So now we can rearrange and find acceleration. So we can say acceleration, we can just divide everything by mass. You know what I mean? So you do this, and you see that we have gravity minus EA divided by ml x is equal to our acceleration of acceleration. Hell yeah. Okay. And I guess at some point, this can't answer my question now, because at some point I want to know when the acceleration is 0. You know what I mean? Because we're going to have a positive, this thing's going to be 10 and this thing's going to be 0. But at a certain point, this one's going to be 10 and this one could be negative 100. You know what I mean? We've done the problem from part 1, 2, and 3 that this could be like negative 3,000. So at a certain point, this one's going to be in the negative direction, which means that we're going to, and what's the definition of acceleration? Change in velocity, change in time. So in free fall, we're going to have a change in velocity in this direction by 10 meters per second every second. But if it's negative, hey, we're going to have a change in velocity in that direction. But we're going to have some sort of velocity in this direction, but now we're going to change its velocity. We're going to slow it down, you know what I mean? And then we might come to a dead stop, and that's the end of the problem. But then, you know what I mean, hey, we still have an acceleration up that way, so we're going to, that's where this thing's going to rebound and go back and forth, you know what I mean? And it's going to cross this point where acceleration is 0. So sometimes people are just really good at looking at an equation and being like, yeah, no duh, no duh. I know exactly when this is equal to 0, so let's do that. We can just solve for 0, and we can say that gravity is equal to EA divided by ML x, and we want to figure out when that x value is. So we go x over here. I'm sorry I rearranged, but ML is going to go up top. So we're going to have GML divided by EA. That is going to give us the value, and I don't think it's going to be halfway. You know what I mean? So let's figure out what it is. We got 9.81. We got a mass of 20, a length of 2, 2010. 10 to the 9. See how I did that? Because I'm going to do that in my calculator. We got pi divided by 4. 0.015 is our diameter in square. So hell yeah, let's just do this real fast. 9.81 times 20 times 2 divided by 210 divided by 10 to the 9 divided by pi times 4. And you see how I did this? Because if this is all divided by pi divided by 4, that's the same thing as multiplying by 4 divided by pi. So pi is still downstairs, but we're multiplying by 4. And in the calculator, it can only do one thing at a time. We're dividing just by pi. This does not say this. This does not say divide by pi and divide by 4. The product of those. No, it just says divide by pi, be done with it, and then up top multiply by 4. Hell yeah. And then we got to multiply by 0.05 squared. Cool. And so this happens real hell the fast. And I just got to double check because I have no check on reality when this is going to happen. But we can have Excel. That's where doing the next step in Excel, which will be the fun part, will pretty much give us all our checks on reality. And it's as simple as just throwing in the equation for acceleration. You know what I mean? G minus EA divided by MLX. And if you throw this in, you know what I mean? Hey, then you get an acceleration. And so let's double check this. 9.81 times 20 times 2 divided by 210 divided by 10 to the 9 divided by pi times 4. Oh, see, I messed it up again. I don't know why the hell I'm messing this up every time. You know what I mean? It's the same error, but you know what I mean? I was getting the wrong answer, so I should have put asterisks on the page. You know what I mean? Mentally, I was doing that. I was just like, oh, hell no. So we went back and we found our answer. Okay, sweet. So now times 1,000. And yes, this happens. That's so cool. So now we know we have a linear, it's kind of a linear relationship, is that this thing's going to get up to a max speed, and then it's going to slow down. You know what I mean? So I find that fascinating, even though a spring has no force, you know what I mean? And then so it's going to be in free fall, and then a spring has a max force. But because of that relationship, I can't even explain it. But the change in velocity, I mean, where the velocity is max is at delta L divided by 2. That's what this just said right here. So let's do this. Let's go back to our kinetic energy equation and say that we have 1/2 mv. Okay, so if this is the total energy, you know what I mean? And then we want to find the kinetic energy at the half of change in L. Well, that means that we're still going to have some potential energy. We're going to have 1/2 mg change in length. And I don't like when people, like even the textbooks do this. It's like, hey, that was a dumb way to write that. We have mg, and then the change in length, the height is change in length divided by 2. It's a better way to write that. So that's going to be our potential energy. We still have that much potential energy until we hit our datum. But now we have some sort of velocity, 1/2 mv squared. So now these two things are equal. The energy input of potential energy is going to equal to the kinetic energy plus the remaining potential energy. Okay, hell yeah. So let's do that. So we're going to have mg change in length is equal to mg change in length divided by 2 plus 1/2 mv squared. Cool. So we have a mass everywhere, even though that was probably not the first thing I wanted to cancel out. I really wanted to say this was mg change in length minus 1/2 of that. So so let's say we didn't cancel out masses. Over here, you're going to have just 1/2 mg change in length, and that's going to equal 1/2 mv squared. Now it just logically makes sense to cancel out the halves, cancel out the masses, and then you have g change in length over here, and we know that value for change in length, and we have v squared. So all we got to do is just take the square root of that side. So velocity max is equal to the square root of g change in length. I don't even have change in length in my calculator. Holy Toledo. Yeah, let's go get that value. I mean, we just did it. It's right here, times 1,000. So this is my change in length, and we got to get it back into meters. So divide by 1,000. I'm going to store that as alpha. I'm just going to do alpha d. I'm going to say my change in length is alpha d in my calculator. And cool, so times 9.81, and then the square root of that. So we get a max velocity of 0.01 meters per second. So this will be a check on reality we'll look for in Excel. You know what I mean? Like that's imperceptible velocity, but we just know that this mass is going to get up to that velocity, and then we need to slow it down. You know what I mean? So there you go. Okay, hell yeah. So one more page, and we should be done, and we'll do this in Excel. Alright, hell yeah. And let's get messy, you know what I mean? At this point, we just kind of know what the hell we're doing. I don't have another sheet of paper with this information on, and we already started here. Well, we're going to get hella messy, but we got an equation for acceleration. We're going to get that number. So we have to use the equation for acceleration as change in velocity, change in time. You know, in Excel, I'll just say this is just dv dt, and then we have three things. The only thing about this is it has to be the average acceleration. And if we take a small change in time, well, this acceleration really isn't going to be changing much between there. So hell yeah, we have a check on reality that this will be the average acceleration. You know what I mean? But this is one of those scenarios where we're just not in free fall. We don't just have g as our acceleration. Our acceleration is going to be changing. It's going to be positive and then go to negative. But at any small change in time, the acceleration is basically the same at that point. But keep that in mind when we get to the equation of velocity is change in position, change in time. Then we definitely need to use the average acceleration. It is dx dt. Okay, cool. So we have acceleration. And what we want to know is because acceleration is going to be a change in velocity, in meters per second, divided by a change in time, you know what I mean? Well, we can find that change in velocity given a small amount of change in time. So you have three things here, and we just rearrange for dv. dv is acceleration times dt. And then we'll find that. So we get this column for change in velocity. Cool. And it's going to be this number times a 10,000th of a second. And I might have to increase this to a 100,000th of a second, you know what I mean? But that's going to be our change in velocity. This cell is going to be 0, the upstairs, plus, hey, our change. Cool. And so that's where our change in velocity comes from. And we're going to do the same thing. We need a change in position. So then, but you do have to throw in this column of average velocity, because we now know our velocity is 0, and we went to here, and you definitely need to take the halfway point between them. This is crucial for this scenario. And it kind of goes back to the car analogy, going 0 to 60 miles per hour in 1 hour. If you get into a car, and for an hour you just decide to slowly increase your speed, I think we can mentally imagine this. But it's like you had an average velocity of 30 miles per hour. So if you want to know how far you went, you take that 30 times your 1 hour. Same thing here. If we want to know how much distance we're going to travel between going from a dead stop to some sort of velocity, we can't just take this velocity as our max, and I think that explains it. We can't just say we went 60 miles per hour for an hour, and just like we can't say we went 100 miles an hour for an hour. But if you actually did this change in time to be so small and just said, nah, you could get a fairly accurate answer, I think, even if you just took, because put it this way, if this change in velocity is so minusculely tiny, then you're saying, hey, the acceleration is just that. Because even when we do this, I'm just going to take the acceleration at that point, but that is going to be the acceleration at that point. But then the acceleration at the next point is going to be different. But even in my Excel setup, I'm not averaging the two of them, you know what I mean? But I guess I just do here, you know what I mean? I always do it here, and maybe I can up my Excel game and actually average the acceleration between 2 points. We'll see. But this will get you there fairly accurately. So the average acceleration is just whatever this is, it's just halfway, and the equation for that is whatever the lower value plus the upper value is, so you add them, 0 plus 60 divided by 2. That's the generic equation for finding the average number between two numbers. Cool, so that's going to give us the average velocity, and then we use this equation. Average velocity is change in x, change in t, and again, we have an equation with three things, and we can rearrange. dx is average velocity dt. All I did was take this dt, throw it up top, and I got an equation for my change in x. Cool, and then once I do that, what's my time frame on this? Well, it's still a 10,000th of a second, so I'm taking that average velocity, multiplying it by 10,000th of a second. You know what I mean? It would be like, hey, I'm going 60 miles per hour, but now I'm only going to go for a 10,000th of an hour. It's just like, well, you went a very small portion of a mile. Okay, so, and then you're going to get a number for change in x. So this value right here is going to be 0, the upstairs plus that new change in x. And now we just start the whole process over again. Since we have a new change in x, our acceleration is a function of that x value. You know what I mean? And at the halfway point, these two things are going to equal, and at the double it point, you know what I mean? That's the crazy thing. Okay, so that's where I just didn't think. I guess I get it, but that's really bizarre. Yeah, that's messing with my mind right now, and it should be intuitively obvious, but it's not. That means that at our change in length of 0.01, whatever it was, what would we alpha d? Times 1,000, this many millimeters, 0.0106 millimeters. At that, times E times A divided by mass divided by length, that is going to equal 2 times gravity. That's it. You know what I mean? Because at the halfway point, it's going to equal gravity. At the 0 point, gravity is going to be 10. So yeah, it's just so fascinating how that balances, and like it should be obvious, but it's just that simple integration of, like, you know, when things are linear, but you just not sure that they are. So let's at least do that one. Just real briefly in our calculator, we're going to go 210 times 10 to the 9. That's going to be alpha e times parentheses pi divided by 4 times 0.015 squared. Hell yeah, I got the squared on the acceleration, I mean the area term, divided by 20 divided by 2. Cool. And this, and then, oh, don't we have to multiply by d? Yes, and then multiply by alpha d. And hell, whoa. That messed with me. That's gonna be where or did we not do this right? Didn't we say oh, yeah. Okay, I'm messing two different problems up. One is if you just statically put this weight and then make this change in length, the change in length is 0.0106 millimeters. But going back to our problem, if you drop it from 0 height, you double it. So you're going to go 0.02149. So holy hell. So my alpha D, I need to multiply this by 2 and store it as alpha E. So my change in length for this problem is alpha E. This is the static. If I just statically loaded it, we'd get down to there. If I dynamically loaded it, dropping from 0 height, I go past this point, and then it oscillates back and forth, and then if there is dampening, it settles right at that, and they call that statically loaded change in length. Okay, so hell yeah. So now let's redo this one. Instead of using D, we're going to get alpha E, and duh, we get twice gravity. That's what I was showing. It's just so fascinating when I get something cool and then I just make a mistake. But doing those cool things helps me identify where I was kind of making mistakes. Okay, so now we have that, and now we're just good to go. We're going to throw this into Excel, and we're going to find that value. that was kind of an interesting one. We're obviously going to find the max change in length. And where the hell is that going to be? That's when our velocity is finally back to 0. It's going to get up to some max, and we're going to register that was at the halfway point. So this is also going to be 0.0106. And then obviously we're going to see that our x value where velocity is 0 is going to be double that. So alpha e. That's going to be 0.021147. Cool. All right, so let's throw this in Excel and catch you on the flip side. All right, hell yeah. So we're back, but I think we're pretty much done. You know what I mean? We definitely fully now understand that this thing generates velocity. It's falling under free fall for just a split second at the halfway point. You know what I mean? Because we have alpha e is the full, you know what I mean? Alpha e 1000, alpha d 1000. So those are the values at the halfway point at 0.01. Oh, they're already in here. Is that? Yeah, at 1.057. That's our halfway point, and we see our velocity is maxed out. So that's kind of what we found. And then at 2.11. Yeah, and this is just a little bit higher because we're only taking yeah, and then I bet you we could get a little bit better. I never even thought to. I just don't know if you could do like a circular. Try not to do a circular reasoning. I mean, you could have like two different x values, like one for taking the acceleration, but then once you know the new acceleration, you know what I mean, you can average those two and then use that. But I don't know, you know what I mean, or you can just change your time value to be a little bit tighter and you get more accurate. But I just think doing it in this is totally explaining F equals ma. It's getting an equation for acceleration. That's going to be the net force divided by the mass, and that's what we did for acceleration. And then you just see how that plays out. You see that if you have some initial velocity, well, that acceleration is going to change that initial velocity. You know what I mean? So that's the only thing about our problem is our initial velocity was 0, our position was 0, and yeah, I just think it's very fascinating. But heck yeah. And again, you know, this is falling under free fall until that spring provides a force, and the force is going to be equal right when the velocity is max at the halfway point, and then this thing is going to come to a stop, and that's going to be our max change in length. And for just what we're doing, we're showing that that's twice the value of just slowly resting this mass and sinking it into place. If you do that, your change in length is not impacted. So this is the least amount of, and it's not the least amount of impact. I mean, you could also, if this weighs 44 pounds, you could have, you know, you don't have to hover it. You could have 22 pounds, you know, on it, and then you're holding 22 pounds, and then you could instantly let that go. You know what I mean? And that would be the same problem at you know, you'd have to say at 22 pounds, what's your initial change in length there, set that datum equal to 0, and then you could do the problem like you're just impacting it with 22 pounds of force. But anyway, I think I'm done with this one. And yeah, it's pretty cool. That's exactly what I wanted to do. I wanted to show how the F equals ma approach works when energy, man, these energy equations are so simple and so useful, but you know, if you don't know where they come from, I think that's going to do you a disservice in the long run. Alright, so hell yeah, thanks for joining me, and that's a video.